So reviewing it, sort of the pros and cons. What's the biggest pro of a Kalman filter? It's all listed here as one, but look, it's just very simple. You know those equations, you just implement them, you write them, it's compact, it's efficient, it works pretty well. You have to sometimes tune some things, like you never want to let your process noise get too small. It's much better to overestimate process noise than under. Why? Because if you, for example, suppose you didn't think there was any process noise at all. You thought this point is just there, okay? So you're taking measurements. Well, if there's no process noise, remember, every time you take a measurement, your uncertainty goes down. Eventually, you'll go to an uncertainty of 0, and you'll stop listening to your measurements. So it's always good to have a little bit of process noise. So there's some tuning to make it work, but in general, it's pretty clean. The biggest problems with it are that it's, first of all, fundamentally a unimodal distribution, right? I've basically got a Gaussian, which means I basically have a single hypothesis, right? And it's some uncertainty within that hypothesis. There are some other issues here. Remember, we have this linear model. There are ways of fixing that. There's something called the extended Kalman filter, which basically just takes, for those of you who care, you linearize about your current point. That's like taking a Jacobian around the nonlinear system. You currently estimate it linearly, update, then recompute your equations in the nonlinear prediction. So the linearity part is not that big of a problem. But this problem of having a single hypothesis, okay, that's a Gaussian, that doesn't work so well sometimes. So the question is, what should you do if the world's not Gaussian or it's not even unimodal? And the answer is, you should come back next time, because we'll tell you then.